So the way that all modern graphic cards do this is to use a depth buffer. So what's a depth buffer? Well, on your screen, you see a color buffer. So this you think of as the pixels on your screen. They store RGB, and we have some picture. But stored along with it and hidden where we don't see it is a depth buffer. And this depth buffer says how far is it to each object. And black is a close depth and white is a far depth in this. So these objects are further away, these objects are closer, and it's basically saying what's in here. So if we zoom in, the color buffer's just got what we think. The depth buffer, every one of those pixels has got a value, is stored. And this is a numeric value, 1 meter away, 10 meters away. Since we don't have meters, it's just the units, right? So we would be storing the -1 to 1 that you've been writing into your Z values so far and into this. So how we're going to use this? We're going to use it to keep track of occlusion, what's in front of what. So our starting state is a blank pixel grid, right? So in this set of slides, we're drawing the pixel grid this way. We have samples. So each pixel is a sample, and we'll see why samples, because remember later earlier, we talked about super sampling and the notion that there might be multiple samples per pixel. So these things are samples or fragments that we're going to store this information in. And we're going to initialize it to everything is far. Everything has got whatever is the furthest distance in here when we start out. So then we're going to look at an example. What happens when we stick some triangles into this thing? So we start with this yellow triangle. It's going to be at depth 0.5. We don't have anything in the color buffer yet. We go figure out which samples are turned on. This is rasterization, right? Which things are overlapped by this yellow triangle. And then for each one, we do a test. We look at the previous value, and we look at the value for this thing that we're about to render, in this case, 0.5. So we have far, and we have 0.5. And then we check if they pass the test. And the red ones here, meaning all of them, pass the test. So we're going to update, and we're going to put those colors into our buffer. So now this is our color buffer. Since it was a yellow triangle, we store these yellow things. Remember, we don't store the whole triangle. After when we're doing this, we're doing it at the sample or fragment or pixel level. So each one of these pixels is now storing this color. And that's all the information that we have about the triangle at this point. But we've also stored in the depth buffer this medium gray that was at 0.5 distance. So now we come along with another triangle, this blue one, and it's at distance 0.75. So it's further away than the yellow one was. So which samples does it turn on? All the samples that are inside of here are inside, and we're going to run the fragment shader for each of these samples. But when we're done with the fragment shader, we're going to have some output Z value, and we can test this output Z value against the previous ones. And these red ones are the ones that pass the test. These others don't pass the test because they were set to 0.5 before, and 0.5 is closer than 0.75. So therefore, we don't write into them. So what's our update afterwards? Our color buffer has been updated. The rest of the triangle did not update these other pixels because it was behind. And our depth buffer now has stored this further away 0.75 value in these pixels. So we come to another triangle. Here's a red triangle. We're now at 0.25. So we should be closer to everything. And everything is colored red because it passes the depth test. And so what do we end up with? We turn all those pixel samples to be red, and we update this buffer so black is very near the 0.25, and this is what's in our depth buffer afterwards. So we repeat this for all of the triangles. So what's this algorithm look like? It's a really simple algorithm. We have some notion of passing a depth test, and most of the time it's a very simple thing. If our new thing is less distance than the old thing, then we're going to say true, right? And so then what do? So our depth test for a triangle, and this is, we're going to check if we pass the depth test for our new triangle for each sample, not for the triangle as a whole, but for all the samples in the triangle against our depth buffer. Our depth buffer is just an image, right? So we parameterize X, Y as an image. And then if it's the closest thing, we update the depth buffer, we update the color buffer, and we write it in. That's it. This is the Z buffer algorithm. So this is what's implemented in modern graphics card. Why do we even bother to talk about something so simple? So historically, there's been all kinds of complicated ways to do figuring out which object's closest, and we'll talk about some of those later. This is implemented in hardware because it is simple, right? So it should look pretty easy to you. It is easy. That's why it goes in hardware. So let's just check if it works in all the cases. What about interpenetrating services? So these two triangles are going through each other. Is this gonna do the right thing? Of course it's gonna do the right thing because we're only looking at samples. Each point is independent. Who cares they're interpenetrating, not interpenetrating? All we care is what was the depth at that pixel by the time we came out of the fragment shader. So we're typically setting our position in the vertex shader. It turns out the fragment shader is allowed to mess with that position also, which is why this test is done after the fragment shader. What if we had super sampling? So we have an edge here. Here's all of our samples. Those samples don't need to be per pixel, right? I could have multiple samples within a pixel. This is the super sampling we talked about before. Works fine. And in fact, this is commonly done. So we run our fragment shader and we do our depth tests at each sample, at each fragment. What finally ends up on the screen, we're gonna average these things. So this is what we talked about in super sampling. We're gonna average these things. If it's all green, it's gonna be green. If it's all yellow, it's gonna be yellow. If it's some mixture, we're gonna get some mixture color. So you're gonna get things that look like this by the time it shows up on the screen. So super sampling, anti-aliasing, okay, works fine with this Z-buffer algorithm. So for the basic Z-buffer algorithm, no problem. We're going to store one depth value at each place, constant memory per sample. So it doesn't matter how many triangles we have sort of a constant memory. In fact, as we step through our triangles, we don't have a complicated sorting. So the sorts you learned in your algorithms class were probably all in log in, this kind of thing. No, we just go to each triangle, we figure out what to do with it, we're done with it. So we're not even in log in, we're order in to deal with all of our things. So it's a very efficient way to deal with sorting what's in front of what.